So in this lecture, we're going to talk about the observability Gramian. The observability Gramian is a way to quantify how difficult it is to determine the initial conditions of some dynamical system if you're only given a sequence of measurements and control inputs and some system model. This turns out to be a really useful property for understanding how difficult it is to estimate the states of your system. Now, before we dive into the derivation of the observability Gramian, let's think a little bit about what a gram matrix is. That'll give us some clues of what we should be expecting. So for a real system, a gram matrix is generally going to look like some matrix transpose times itself. So I'm going to write it out as this fancy O transpose O, because that's ultimately what we're going to find. So we're looking for something with that general form. That has a couple implications. This is going to be a symmetric matrix, guaranteed. It's also going to be positive semi-definite. In the case where that O transpose O is full rank, then it will be positive definite, not just semi-definite. So let's go back to thinking about what it is that we're looking for in our observability Gramian. We want something that tells us how sensitive our outputs are to our initial condition. So let's think about what our outputs are and write out some output energy function that's going to describe all of the outputs that we have access to. So we'll write out the output energy as 1/2, and we're going to do this in discrete time. So the sum of our measurements at each time step transpose times those measurements, and we'll go from k equals 0 to k equals n, some large window in time. Those are all the measurements that we're going to have access to. Now let's think a little bit about what this means. We'll derive it much more explicitly in a moment, but those measurements y are going to be proportional. In this case, we're working with linear systems, so they're going to be linear proportional to the initial condition. That means that that y transpose y is going to be proportional to the initial condition transpose times itself. So if we were to think about what that looks like visually, we can make a plot of our sum of our measurements as a function of the initial condition. Now, because our sum of our measurements is going to be proportional to the initial condition transpose times itself, it's essentially going to have something that looks like a quadratic. It'll have some shape like this. So if we analyze the curvature of that graph, that will tell us how sensitive our output measurements are to our specific choice of initial condition. Or rather, if you made small changes in the initial condition, how much would those outputs change by? That's what we're after. So in order to quantify that, we can calculate the second derivative of that curve. So we can calculate the second derivative of that output energy, and that will give us intuitively what we're after. Now we'll have to derive what that comes out to, but that's what we're interested in. So we're going to take the second derivative, but because we're working with matrices, this is really the Hessian of our outputs relative to our initial condition. And we need to figure out what is that equal to. So to do that, we'll have to figure out first what our measurements are as a function of that initial condition, so that we can then go ahead and take that derivative. So we'll start out by writing out what our measurements are at some time step k. So at some time step k, our measurements will be for a linear dynamical system equal to our C matrix times x at that time step k, plus potentially we'll have some D matrix times some control inputs, depending on what exactly our measurement function is. And we don't know what xk is. We want to write out xk as a function of the initial condition, so that we can ultimately get the measurements as a function of the initial condition. So let's start out more explicitly by writing out that the state at time 1 can be related to the initial condition by the standard linear dynamical system. So ax, initial condition, plus b, and the control inputs at that very first time step. Now we can write out what our state would be one time step later at x2. This is just going to be a times the previous time step, which is x1. So we'll have a times ax0 plus bu0 plus plus bu1. Now we can expand this out and simplify it, and we'll see that we're getting to a rather relatively familiar form. So this can be written out as a squared x0 plus a b u0 plus b u1. Now if you were to repeat this, you'll see a pretty familiar pattern. So let's go ahead and write out what that would be. So for xk, this is going to be a to the k x0 plus, and now I'm going to write this out as a matrix product instead of a sum of individual components. So we'll have a to the k minus 1 times b, and we'll have increasingly smaller orders of a until we get all the way down back to b, and that's all going to be multiplied by our u0 at the very top, all the way on down to u k minus 1. Now, this term here might be kind of familiar. This is, in fact, the controllability matrix. And then we can call this here as the control matrix. So we can simplify this a little bit further. So let's call this thing here the controllability matrix for time step k, and we'll call this thing here the control matrix at time step k. So we can write things out a little bit more compactly then. So our state at time step k is going to be, we can write that out as ak times the initial condition plus our controllability matrix times our control matrix. Now we still have to plug that into our equation for the measurements up here. So we're going to plug that expression into xk right there and then see what we get. So after we do that, we'll have that y of k is equal to c times a k x0 plus controllability matrix and the control matrix. And don't forget, we do have that duk out here. Now, in our output energy function, we need to actually calculate y transpose y. So let's explicitly write out what y is, and then we can write out what y transpose is, and then we can look at what the product of those two is. So if we just multiply out, we'll get that y is c a k x0 plus c times the controllability matrix times our control matrix plus duk. So that means that when we take the transpose, we're going to reverse the order, as that's what you need to do when you take the transpose of product of matrices. So we'll just write all this out so that it's very explicit. All right. So now what we're interested in is the product of those two. But now here we can make a little bit of a simplification, because remember, ultimately, what we're interested in is taking the second derivative of our output energy with respect to our initial condition. So any term that doesn't have two copies of our initial condition in it is going to disappear when we take that second derivative. So we don't actually need to write out all those extra terms. There's really ends up being only one term that matters, and that one term is going to be the one that is the product of these first two terms. All right. So let's write that out. So let's write out that y transpose for some measurements at k times y is going to be equal to x0 transpose, a to the k transpose, c transpose, c a k x0. That's just the product of those first two terms that I wrote out for y. And then there's going to be 8 other terms. But as long as our control inputs u are not actually a function of our state, which is an assumption that we have to make in order to do this kind of analysis, then when we take the second derivative, all those 8 other terms are going to disappear. They're all going to go to 0. So we really only need to worry about that first term that I've written out. So now we can go back to our output energy and plug this in and figure out what's going on. So our output energy is the 1/2 times the sum of those y transpose y's. So that's going to be the sum of our x0 transpose, a to the k transpose, c transpose c, a to the k, x0, plus those other terms. But remember, those are going to go away, so we don't need to bother writing those out right now. So now we can take the second derivative. Now note that the initial condition is not going to change as a function of what time step k we're looking at. So we can pull that outside of the sum. And then when we calculate our Hessian, all we will be left with is what's inside of the sum. The 1/2 will cancel out when we take that second derivative of that initial condition. So the second derivative of our output energy is going to come out to just the sum of A, K transpose, C transpose, C, A. And this here is what we call the observability Gramian. Now it doesn't quite yet have exactly the form that we established it should have at the beginning. So let's think a little bit more about what that sum actually looks like. So if we write this out very explicitly for a couple of time steps, then we're going to get that we have, for time step 0, we'll have A to the 0 transpose C transpose C times A to the 0. Sorry, this should have had an A to the K up there. Plus, then at time step 1, we'll have A to the 1 transpose C A. And onwards out to n, since that's what our sum is going from. I should have written that out, so k equals 0 to n. So that's going to go all the way out to A to the n, C transpose C, A to the n. Now we can write this out a little bit more compactly. So this term here, this is that whole sum. So we can write that out a little bit more compactly as a matrix product, where we have C, CA, all the way on to CA to the n. I'm going to take that matrix, we're going to take the transpose, and then we'll multiply it by itself. And this, if you recall from previous lectures, that C, CA, CA to the n, and so forth, that's the observability matrix. So our observability Gramian is really just the observability matrix transpose times itself. So now we're back to that original form that we expected from the beginning. Now note that this observability Gramian is only a function of A and C. For a linear system, it doesn't matter what control inputs you applied. Those all disappeared when we took that second derivative. For nonlinear systems, the control inputs are going to matter, and we'll have to address that separately. We'll analyze what this actually means and what information we can extract from it in a separate lecture.